Hello students, welcome to our YouTube channel Experience Tutor. Today we'll discuss class 11th physics, work, energy and power. Our mission is to provide free classes on YouTube for all the students of class 6 to class 12 and also students who are preparing for IIT, JEE, NEET, NDA and other competitive examinations. Before we begin, we request you to subscribe, like and share our channel among your friends and relatives, and please click on the subscribe button to support us. Also click on the bell icon to get automatic notification whenever a new video is uploaded. Let us begin the class. So the first question is 6.1, that is the sign of work done by a force on a body is important to understand. State carefully if the following quantities are positive or negative. A. Work done by a man in lifting a bucket out of a well by means of a rope tied to the bucket. So let us see the answer and its explanation. Answer in this case is positive. Explanation. Let us see the explanation. In the given case, force and displacement are in the same direction. Hence, the sign of work done is positive. In this case, work done on the bucket is positive. Is positive. So, let us see the next question. The next question is B, that is work done by gravitational force in the above case. Answer to the next question B is negative, because in the given case the direction of the force vertically downward and displacement vertically upward are opposite to each other. Hence, the sign of the work done is negative. Now, the next one, C. Work done by friction on a body sliding down an inclined plane. So, the answer to this is negative. Since the direction of frictional force is opposite to the direction of the motion, the work done by frictional force is negative in this case. Next question, D. Work done by an applied force on a body moving on a rough horizontal plane with uniform velocity. The answer to this question is positive. Here the body is moving on a rough horizontal plane. Frictional force opposes the motion of the body. Therefore, in order to maintain a uniform velocity, and uniform force must be applied to the body. Since the applied force acts in the direction of the motion of the body, the work done is positive. Next question is E. Work done by the resistive force of air on a vibrating pendulum in bringing it to rest. Answer to the question is negative. The explanation is the resistive force of air acts in the direction opposite to the direction of the motion of the pendulum. Hence, the work done is negative in this case. Let us see the next question. Question number 6.2. A body of mass 2 kg initially at rest moves under the action of an applied horizontal force of 7 Newton on a table with coefficient of kinetic friction is equal to zero point 0.1. Compute the A. Work done by the applied force in 10 seconds, B. Work done by the friction in 10 seconds, C. Work done by the net force on the body in 10 seconds, D. Change in kinetic energy of the body in 10 seconds and interpret your results. Let us see the solution. So, it is given that mass of the body is 2 kg. Applied force F is equal to 7 Newton. Coefficient of kinetic friction mu is equal to zero point 0.1. Initial velocity u is equal to 0. Time t is equal to 10 seconds. Acceleration produced in the body by the applied force is given by the Newton's second law of motion as A dash is equal to F by m, that is equal to 7 by 2, which is equal to 3.5 meter per second square. Now frictional force is given as F is equal to mu mg. Putting the value of mu, m and g, we get 0 0.1 multiplied by 2 multiplied by 9.8, which is equal to minus 1.96 Newton. The acceleration produced by the frictional force A double dash is equal to minus 1.96 upon 2, which is equal to, here 2 is the mass, F is equal to ma. In that formula we get A double dash is equal to 1.96 upon 2. My negative sign is because it is retardation. So now the A double dash is equal to minus 0.98 meter per second square. Total acceleration A is equal to A dash plus A double dash, which is equal to 3.5 plus bracket minus 9.8 minus 0.98, which is equal to 2.52 meter per second square. The distance traveled by the body is given by the equation of motion s is equal to ut plus half at square. Putting the values of u, t and a, we get 126 meter distance. Now work done by the applied force Wa is equal to F into S, that is 7 into 126, that is 882 joule. Work done by the frictional force Wf is equal to F into S, that is minus 1.96 multiplied by 126 is equal to minus 247 joule. Net force is equal to 7 plus bracket minus 1.96, which is equal to 5.04 Newton. Work done by net force W net is equal to 5.04 multiplied by 126, which is equal to 635 joule. From the first equation of motion, final velocity can be calculated as v is equal to u plus at. Putting the value of u, a and t, we get 25.2 meter per second, which is equal to half mv square minus half mu square. Now putting the values, uh, we get half multiplied by 2 v square minus c square, and putting the value of v and u, we get uh, 25.2 whole square minus u square, that is 635 joule. So this one was v, and this is u, initial velocity. And in this way we have calculated the uh, difference in initial and final kinetic energy. Let us move to the next question, 6.3. Given in the figure 6.11 are examples of some potential energy functions in one dimension. The total energy of the particle is indicated by a cross on the coordinate axis. In each case, specify the region, if any, in which the particle cannot be found for the given energy. Also indicate the minimum total energy the particle must have in each case. Think of simple physical context for which these potential energy shapes are relevant. Let us see the solution. So, in the first case, x is greater than a and answer is 0. So, total energy of the system is given by the relation E is equal to potential energy plus kinetic energy. Now, kinetic energy is equal to total energy minus potential energy. Kinetic energy of a body is a positive quantity. It cannot be negative. Therefore, the particle will not exist in a region where kinetic energy becomes negative. In the given case, the potential energy V naught of the particle becomes greater than total energy E for x is greater than a. Hence, kinetic energy becomes negative in this region. Therefore, the particle will not exist in this region. The minimum total energy of the particle is 0. All regions. In the given case, the potential energy V naught is greater than total energy E in all regions. Hence, the particle will not exist in this region. Here x is greater than a and x is less than b and minus v1. In the given case, the condition regarding the positivity of kinetic energy is satisfied only if the region between a is x is greater than a and x is smaller than b. The minimum potential energy in this case is minus v1. Therefore, kinetic energy is equal to E minus bracket minus v1, which is equal to E plus v1. Therefore, for the positivity of kinetic energy, the total energy of the particle must be greater than minus V1. So the minimum total energy of the particle must have is minus V1. So minus x is greater than minus b by 2 and less than a by 2. X is greater than a by 2 and less than b by 2, and minus V1 is the value of potential energy. In the given case, the potential energy V0 of the particle becomes greater than the total energy E for B minus for x is greater than minus b by 2 and smaller than b by 2, and x is greater than minus a by 2 and smaller than a by 2. Therefore, the particle will not exist in this region. The minimum potential energy in this case is minus V1. Therefore, kinetic energy is equal to E minus bracket minus V1, that is E plus V1. Therefore, for a positivity of kinetic energy, the total energy of the particle must be greater than minus V1. So, the minimum total energy of the particle must have minus V1. Let us see the next question. Now, let us see question number 6.4. The potential energy function for a particle executing linear simple harmonic motion is given by Vx is equal to kx square by 2, where k is the force constant of the oscillator for k is equal to zero point 0.5 Newton per meter, and graph of Bx versus x is shown in the figure 6.12, so that the particle of total energy 1 joule moving under this potential must turn back when it reaches x is equal to plus minus 2 meter. Let us see the solution. So total energy of the particle E is equal to 1 joule. Force constant K is equal to 0.5 Newton per meter. Kinetic energy of the particle K is equal to half mv square. According to the conservation law, E is equal to V plus K. So putting the value of E, V and K, we get 1 is equal to half kx square plus half mv square at the moment of turn back velocity, and hence K becomes 0. So therefore 1 is equal to half kx square. Therefore half multiplied by 0.5 x square is equal to 1, and x square is equal to 4, x is equal to plus minus 2. Hence the particle turns back with when reaches x is equal to plus minus 2 meter. Let us see the next question. Answer the following. A. The casting of a rocket in flight burns up due to friction, at whose expense is the heat energy required for burning obtained, the rocket or the atmosphere. Let us see the solution. So the solution is the burning of the casting of rocket in flight is due to the result in the reduction of mass of the rocket. According to the conservation of energy, total energy is equal to potential energy plus kinetic energy. Instead of potential energy, we can write mgh, and instead of kinetic energy, we can write half mv square. The reduction of the rocket's mass causes a drop in total energy. Therefore, the heat energy required for burning is obtained from the rocket. Let us see the next question, B. Comets move around the sun in highly elliptical orbits. The gravitational force on the comet due to the sun is not normal to the comet's velocity in general. Yet, work done by gravitational force over every complete orbit of the comet is zero. Why? Let us see the solution. Gravitational force is a conservative force. Since work done by the conservative force over a closed path is zero, work done by the gravitational force over every complete orbit of a comet is zero. Let us see the next question. Next question is, an artificial satellite orbiting the Earth in very thin atmosphere loses its energy gradually due to dissipation against atmospheric resistance. However small, why then does its speed increases progressively as it comes closer and closer to Earth? Let us see the solution. When an artificial satellite orbiting around Earth moves closer to Earth, its potential energy decreases because the reduction of the height. Since the total energy of the system remains constant, the reduction of potential energy results in increase in kinetic energy. Hence, the velocity of the satellite increases. However, due to atmospheric friction, the total energy of the satellite decreases by a small amount. Let us see the next question. So, D, question number D. In figure 6.13, that is in this figure, he walks the same distance pulling the rope behind him. The rope goes over a pulley and a mass of 15 kg hangs on the other end, in which case the work done will be greater. Answer is in the second case. Why? The explanation is given below. In case 1, mass is equal to 15 kg, displacement s is equal to 2 meter, work done W is equal to Fs cos theta. So here so work done is equal to W is equal to Fs cos theta, where theta is equal to angle between the force and displacement. Therefore, we can write mgs cos theta. Putting the value of mgs and cos theta, we get value as 0, as cos 90 is 0. Now let us consider case 2, where mass is equal to 15 kg, displacement s is equal to 2 meter. Here the direction of the force applied on the rope and the direction of the displacement of the rope are same. Therefore, angle between them is theta is equal to 0 degree. Since cos 0 is equal to 1, therefore work done is equal to Fs cos theta, that is mgs. Putting the value of mg and s, we get 294 joule. Therefore, more work is done in the second case. Let us see the next question. Let us see question number 6.6. A. Underline the correct alternative. When a conservative force does positive work on a body, the potential energy of the body increases, decreases, remains unaltered. Let us see the solution. So, a conservative force does a positive work on a body in the direction of the force. As a result, the body advances towards the center of force. It decreases the separation between the two, thereby decreasing the potential energy of the body. So answer is decreasing. Let us see the next question. B. Work done by a body against friction always results in a loss of its kinetic or potential energy. Let us see the solution. The work done against the direction of friction reduces the velocity of the body. Hence, there is a loss of kinetic energy of the body. Now, question C. The rate of change of total momentum of a many particle system is proportional to the external force or sum of the internal force on the system. Solution. Internal force, irrespective of their direction, cannot produce any change in the total momentum of a body. Hence, the total momentum of a many particle system is proportional to the external force acting on the system. Let us see the next problem. Problem D. In an inelastic collision of two bodies, the quantity which do not change after the collision are the total energy slash or total linear momentum or total energy of the system of two bodies. Let us see the solution. The total linear momentum always remains conserved whether it is an elastic collision or an inelastic collision. Let us see the next problem. Question number 6.7. State in each of the following statement is true or false. Give reason for your answers. A. In an elastic collision of two bodies, the momentum and energy of each body is conserved. So answer is false. Why? Because in an elastic collision, the total energy and momentum of both bodies and not each individual bodies is conserved. Let us see the next question. B. The total energy of a system is always conserved no matter what internal and external force on the body are present. Let us see the solution. The answer is false. Although internal force are balanced, they cause no work to be done on a body. It is the external force that have the ability to work. Hence, external force are able to change the energy of a system. Let us see the next question. C. Work done in the motion of a body over a closed loop is zero for every force in nature. Let us see the solution. The answer is false. Work done in the motion of a body over a closed loop is zero for a conservation force only. Next question, D. In an inelastic collision, the final kinetic energy is always less than the initial kinetic energy of the system. Let us see the solution. The answer is true. In an inelastic collision, the final kinetic energy is always less than the initial kinetic energy of the system. This is because in such collision there is always a loss of energy in form of heat and heat, sound, etc. Let us see the next collision. Next question. Question number 6.8. Answer carefully with reason. So first is A. In an elastic collision of two billiard balls, is the total energy conserved during the short time of collision of the ball, that is when they are in contact? Let us see the solution. Answer is no. The reason behind is in an elastic collision the total initial kinetic energy of the ball will be equal to the total final kinetic energy of the balls. The kinetic energy is not conserved at the instance the two balls are in contact with each other. In fact, at that time of collision, kinetic energy of the ball will get converted into potential energy. Let us see the next question. Next question is B. Is the total linear momentum conserved during the short time of an elastic collision of two balls? Let us see the solution. The answer is yes. In an elastic collision, the total linear momentum of system always remains conserved. Let us see the next question. Now, question number C. What are the answers to A and B for an inelastic collision? Let us see the solution. Answer of A for inelastic collision is no, and answer of B for inelastic collision is yes. The explanation is as in an inelastic collision there is always a loss of kinetic energy, that is total kinetic energy of the billiard balls before collision will always be greater than that of after collision. The total linear momentum of the system of billiard balls will remain conserved even in the case of inelastic collision. Question number D. If the potential energy of two billiard balls depends only on the separation distance between their centers, Is the collision elastic or inelastic? Note, we are talking here of potential energy corresponding to the force during collision, not gravitational potential energy. So let us see the solution. Answer is elastic. Reason behind is in the given case, the force involved are conserved, conserved are conserved. These is because they depend on the separation between the centers of the billiard balls, hence the collision is elastic. Let us see the next question. The next question is 6.9. A body is initially at rest. It undergoes one-dimensional motion with constant acceleration. The power delivered to it at the same time t is proportional to a t to the power 1 by 2, 2 t, 3 t to the power 3 by 2, 4 t square. Let us see the solution. The answer is 2 t. Let us see the explanation. Mass of the body m, acceleration of the body a. Using Newton's second law of motion, the force experienced by the body by the equation is F is equal to ma. Both m and a are constants. Hence, force F is also a constant. F is equal to ma is equal to constant. That is equation number 1. Now, the velocity v1 is acceleration. For velocity v1, acceleration is given as, or for velocity v, acceleration is given as a is equal to dv by dt is equal to constant. dv is equal to constant into dt. Velocity, therefore v velocity is equal to alpha into t, where alpha is another constant. This is equation number 2. So v is proportional to t. Power is given by the relation P is equal to F into V. From equation 1 and 3, we have power is directly proportional to T. Hence, power is directly proportional to time. The answer is T. Let us see the next question. The next question is 6.10. A body moving unidirectionally under the influence of a source of constant power. Its displacement in time t is proportional to 1 t to the power 1 by 2, 2 t, 3 t to the power 3 by 2, 4 t square. Let us see the solution. Answer is 3 t to the power 3 by 2. Let us see the explanation. Power is given by the relation P is equal to F into V. Instead of F, we can write ma into V, that is mv dv by dt is equal to constant, say k. Therefore, v dv is equal to k by m dt. Integrating both the side, we get v square by 2 k by m multiplied by t. Therefore, v is equal to under root 2k t by m. For displacement x of the body, we have v is equal to dx by dt. Putting the values, we get under root 2k by m t to the power half. dx is equal to k dash t to the power half dt, where k dash is equal to under root 2k by 3, which is equal to a new constant. On integrating both sides, we get x is equal to 2 by 3 k dash to the t to the power 3 by 2. Therefore, x is k proportional to t to the power 3 by 2, which is the answer. Let us now this is the end of this chapter today. This class today will do next problems or next questions in the next class for the same chapter. Before we close, we request you to subscribe, like, and share our channel. Please click on the subscribe button to support us, and also click on the bell icon to get automatic notification whenever a new video is uploaded by us. Thank you for supporting us and watching our videos. Thank you very much.